Hello one and all. Welcome to Chemical Kinetics. We are about to start with the 13th class of Chemical Kinetics, wherein we'll be focusing majority of the class on problems. Before we continue with the 13th class, in the 12th class ending, there was some technical abrupt connectivity of the live stream. So let's slightly revise a few points that we are supposed to be doing in the last 10-15 minutes of 12th class, and then we'll continue with the 13th class. So let's start with where exactly we stopped in the previous class. So we were talking about this in our 12th class. So let's discuss about these things even more clearly and then continue with the further discussions. I'll go like this. Now let's talk about two cases. We'll be doing problems on these things today. So that becomes a good revision as well. So assume at a temperature T1, I have a rate constant K1. If it is a first order, then I can have K1 is equal to 0.693 by T half 1. At temperature T2, I have a K2. We decided in the previous class itself that influence of temperature on K can be by two parts. First by collision frequency, the other one by fraction of active molecules. So fraction of active molecules is the dominant factor when compared to collision frequency. So we assume A1 and A2 in both the cases is same as A and continue. So log K1 to base C is minus EA by R into 1 by T1 plus log A to base C. In a similar way, log K2 is minus EA by R into 1 by T2 plus log A to base C. Subtract the second one from the first. So that I'll be getting a plus here. These two get cancelled. So EA by R into 1 by T2 minus 1 by T1. So ln K1 minus ln K2 is equal to EA by R into 1 by T2 minus 1 by T1. So that's what we get as 1 by T2 minus 1 by T1, or T1 minus T2 by T1 T2. So if I have K1 here, you will have T1 minus T2. If I have K2 here, I'll have T2 minus T1. So proportionately it will change. So ln K1 by K2 to base C is EA by R into T1 minus T2 by T1 T2. When I convert this base to base 10, I'll be getting 2.303 to the other side. So that I'll be getting log K1 by K2 to base 10 is nothing but EA by 2.303 R into T1 minus T2 by T1 T2. So again, here also units of R and activation energy have to match properly. So proper units, just like the influence of catalyst on the rate constant and the rate. Similarly, I'm writing here. So when I talk about here, we wrote K1 by K2, right? So this K1 by K2 can also be written as R1 by R2. So R is equal to K into concentration of A to the power N. As temperature increase, K increase, so R increases. As temperature drop, K drops, so R drop. These changes can happen for both exo as well as endothermic in the same way. Both exo and endothermic changes. Endothermic reactions behave in the same way. So this is applicable for both equally. What do you mean by that, sir? For exo it drop, for endo it rise. No such thing. For both, endothermic rate increases with rise in temperature. For exothermic, rate increases with rise in temperature. So in such situation, we can compare one point here. When you get whether it is exo increment or endo increment, that we can talk later. As of now, we have one more point to note. As temperature increase, fruitful collisions or fraction of active molecules increase, thereby K increase and R increases. So this is a point. Now let's continue this discussion in a slightly theoretical manner here. Assume I have two cases where activation energy is less in the first in one reaction, if activation energy is more in the second reaction. T1 T2 are same for both the reactions. For same rise in temperature for both the reactions, so temperatures are same, rise in temperature is same. So what does it mean? This entire bracket is same. When entire bracket is same, denominator is same. So left hand side won't be same because one reaction has got EA lower, the other reaction has got EA higher. So the one that has got a higher activation energy will show a huge change in the rate constants, huge change in the rate. So activation energy, if it is high, that remains the same for higher activation energy as well as lower activation energy. So the reaction which is having higher activation energy will show a considerable rise in rate constant K, a considerable rise in rate of the reaction when compared to a less activation energy containing one. Means activation becomes relatively easier for such normal reactant molecules. So that's a point. So for same bracket, means for same rise in temperature, that reaction which has a higher activation energy will show a huge change in rate, or you can say rate constant. So that's a point. Let's go back to gaseous state, borrow some points from there, and then discuss about one important graphical analysis. It's as follows. In gaseous state, we have one graph, distribution of velocities in different molecules at a given temperature. First, let's talk about at a given temperature. At a given temperature, in a container, you'll have different molecules. Those all molecules will have different velocities. Those velocities will range from a minimum value to a maximum value. And how are these velocities getting distributed across molecules? That's what you call as distribution of velocities in different molecules, or you also call it as distribution of molecular velocities at a given temperature and varying temperature. So let's talk about the same. We carry that, but now we replace this velocity word with energy. Means what? At a given temperature, different molecules possess different energies. Some molecules possess less energy, some molecules possess medium energy, some molecules possess very high energies. Just like when we conduct an exam in a chapter, students will be getting marks. For example, if I were to conduct an exam for 100 marks, students will be getting marks. There will be some students who will be getting marks close to 20. There will be some students who will be getting marks close to 90. So if not 90, the majority will be crossing over 80 if it is a seriously studying student, or if a topic is already being taught in a lower level and in the next higher level the topic is taught. So that's a different issue. But as of now, we have different possibilities there. Means there are three cases. One, very low marks, number of students who are getting very low marks is less. Number of students who are getting very high marks is also less. But those students who are going to get marks in middle, means intermediate marks, the number of students who are going to get the intermediate marks will be higher. So, and obviously that depends on whether you have completed that particular concept in a lower level and then you are reading the concept in a higher level, or you are continuously reading a concept from a lower layer to a middle layer to a higher level. So these are the different points. So let's forget about those things. Whatever is the case, means whatever is the case in the sense whether you heard that concept in your lower level and then you are updating the concept in the higher level, or you are reading the entire chapter from ABCD to the ending, the distribution of the marks will be like this only across molecules called students. So how will that distribution be? It's as follows. This graph might have given you a clear picture of what exactly we are about to do. You take up any subject. Now let's talk about a few points in this graph first related to our chapter, and then we'll talk about analogous discussion, just like jumping over the wall. We'll take example that I have picked up. In the same way, I'll pick up one example related to conducting an exam for 100 marks, and then looking into the number of students who are getting less marks, number of students who are getting very high marks, number of students who are getting intermediate marks, or middle zone of marks. Those things we'll talk. So let's talk about what is there in gaseous state on x-axis. In gaseous state on x-axis, we are talking about velocities. In the gaseous state, we have Ni by n. N is number of molecules who are having a specific velocity. N is the total number of molecules which are existing. Ni is the number of molecules having a specific velocity. N is the total number of molecules that are present in a container at a given temperature. Let's talk about it at temperature T1. Let's talk about this graph first and understand the distribution. So before you understand all these things, let's go back and analyze the following. The first one. Assume we conducted an exam for 100 marks. It's a 10 marks dot, 20 marks dot, 30 marks dot. I'm taking marks on x-axis. I'm taking fraction of students who got that particular marks on y-axis. So this is 10 marks, 20 marks, 30, 40, 50, 60, 70, 80, 90, 100. So these are the 10 dots that I kept on the x-axis, saying that these are the marks. And I'm saying number of students, which is Ni, who get 10 out of a total of, say, something like 50 students are there. Denominator will be 50. There will be 2 to 3 students who will be close to this 10 marks. So 2 out of 50, or say 5 to be simplifying easier. So 5 students will be having close to 10 marks, 10 to 20 marks zone. This 10 to 20 marks zone will be 5 students, in the sense 5 by 50 is a fraction. And there will be 90 to 100, something like 2 to 5 students will be there. Assume they are also 5. So if that is also 5, you can't have entire set of students existing between 10 and 20. You can't have entire students existing between 90 and 100 or 80 and 90. So you'll be having distribution of marks across different students. How will the distribution go? This is how the graphs go. Whether you write an entrance exam or you write an IP exam or you write any of these. Only thing is the exam level, as I said in the previous case, exam level, if it is your 11th class board exam, then the distribution goes much close to the right hand. So we talk about those things as we go along. So as of now, that y-axis is a fraction. Fraction of students who are getting 10 marks, 20 marks. Fraction of students who are getting 30, 40, 50, 60 will be more. So that's what this is saying. So the fraction of students who are getting 10 marks will be less, like this. The fraction of students who are getting 20 will be slightly better. The fraction of students who are getting between 30, 40, 50 will be very, very high. 40, 50, 60, 70. They are the ones which are going to cover this entire graph. And the fraction of students who are going to get beyond 80 will always be less. So see the graph that has fallen. So this is the graph that we are talking. What did the graph tell us? The fraction of students who are getting less marks is less. A fraction of students who are getting very high marks is also less. Fraction of students who are getting intermediate or in between minimum and maximum, that fraction will be higher. Same thing even with the velocities in the gaseous state. It's a velocity. Lower velocity containing fraction will be less. Higher velocity containing fraction will be less. Whereas intermediate velocity containing fraction will be higher. Now what will happen? Assume marks have come out and the faculty has taken the marks list and you are learning the chapter for the first time. When you are learning chapter for the first time, you haven't learned about the chapter definitions also, anything in your previous discussions. First time you are exposed to the chapter. So you have given one exam, you got this distribution wherein this maximum was found to be something close to 40-50. Now the faculty has taken the marks list to the exam, to the classroom. Now there are two types of motivating students. One, moral sciences, which is called as soft motivation, and a harsh motivation called as going on slapping and scolding badly. So slapping and scolding or moral sciences, whatever it is, if the students are working better, thinking that this is for the first time that they are learning, for that just the first examination or the second examination, they have to be going a long way, so they have to be doing excellently well in the due course of learning chapters, because these are all new chapters that they are learning. Then if they continue like that with that thinking, then that moral sciences will transform themselves into rise in energy. Means when we increase, if I slap the students who are getting lower, assuming is no harm. So when we assume that the students who have got lower marks are being slapped, and I increase their focus in the class as well as the homework part and check their respective homework part in the due course, temperature increased in them. So temperature is increased from T1 to T2. Now what will happen to the energies in the molecules? So the distribution changes in a slightly different way. So what happens to fraction of students who are getting less marks? That fraction will drop. Then what happens to fraction of students who are getting relatively better marks? This fraction will rise. So energy increased. Energy increased in whom? In the natural work of a student. So fraction of students who are getting lower marks is dropping. Fraction of students who are getting higher marks is rising. And what happens to fraction of students who are getting that 40 to that 30, 40, 50 zone, that is moving to higher marks, 50, 60, 70 zone. So 70, 80, 90. So as the student starts working more and more, they'll get acquainted with the concept. In the due course, they'll lose some time. First time they might have learned. The second time when they do apply, they get better marks. So the same way, that's what I said. When you learn a concept when you learn a chapter in a lower level, immediately when a faculty teaches in the next higher level and the exam is conducted in the lower level or in between the two levels or a higher level, student feels relatively comfortable in answering such questions. So the same way here also. So in the due course of time, we'll understand what exactly does it mean. So we talk about them in the due course of time. As of now, when the temperature is increased, the energy of the molecules keep go on rising. So what happens to fraction of molecules which are having lower energy? Drops, because you have increased the temperature. Now what happens to fraction of molecules which are having very high energies? Obviously fraction increases. Then what happens to fraction of molecules which are having intermediate energies when I go on increasing the temperature? Just like slapping the students or moral sciences in the classroom after first exam. So obviously that fraction of students who are getting less marks, fraction of molecules which are having lower velocity in the gaseous state. Now in the kinetics, fraction of molecules which are having lower energy drops. Fraction of molecules which are having higher energies rise. Why is it dropping? Because it is getting distributed across higher energies. It's not dropping, the peak is not dropping, it is flattening to the right hand side, means higher energy zones. So means it's a rise in performance of a student. Overall section is going on doing relatively better. So when we talk about a fraction of molecules having lower energies drop, fraction of molecules having higher energies rise, fraction of molecules having intermediate energies drop, but that rises to a higher energy levels. So why did we learn all these things? Let's get back to the kinetics part. Now when I consider the threshold energy and slightly higher energies, slightly higher than the threshold energy, assume this is the threshold of that reaction. I have the case of A, B, C, D. This region A, B, C, D is a fraction of is the total number of molecules which are active and having this energy zone and possessing this energies in them. So this zone of energies is present in these many number of molecules. And anyhow, I said this is the threshold, and slightly higher than the threshold I picked up. So obviously these are the number of active molecules and area under the curve having energy between EB and EA, or you can say EA and EB. Now that is at a temperature T1. Assume I increase the temperature T2. Now what happened to the respective number of molecules? The respective number of molecules in the same energy zone goes on rising. So this entire region, which is ABXY. So ABXY is the number of area which gives you the number of active molecules having energy between EB and EA. ABCD is the area with T1. So what happened to the number of molecules from ABCD to ABXY? The total number of molecules which are active went on increasing. So with rise in temperature, active molecular number increase. So fraction of active molecules increase. That's what we said. Fruitful collisions increase. So as temperature increase, number of active molecules increase. So this, where did we brought it from? You talk about day-to-day life, every weekend exam, every entrance exam that you write throughout your lifetime. The distribution goes like this at a temperature T1. But if you motivate yourself and start performing better, then your lower marks range drop and your higher marks range rise. So that's how it goes. In the same way, we can use that point of either day-to-day life or gaseous state in our kinetics as fraction of molecules with energy on x-axis. So if I say that this is threshold, more than threshold, when I go on increasing the temperature, the area under the curve gives me the total number of molecules in that energy zone. In that energy zone, the total number of molecules have increased, have improved. Thereby we say the number of active molecules increased, fraction increased. Now let's get back to the discussion of this influence. So what are we trying to do in all these discussions is, it's an influence of temperature on rate constant K. That's what our 12th class discussion was. We were talking about influence of temperature on rate constant and rate. So we went ahead like this. We discarded dependence of K dependence on A, and we included only K dependence on exponential part. So that was the temperature coefficient. We talk about these things as we go along, and then we spoke about this point. Slope was minus EA by R if it is ln K to base E. And then we picked up two temperatures, wherein I can write here as, if it is a first order, K1 is equal to 0.693 by T half. So I can also write it as K1 by K2 as T half 2 by T half 1. Be careful, it is T half 2 by T half 1. So I highlight these things as we go along, and then we have come to this. This is the zone that we have seen, which is active molecular number having energy between these two energies. So now getting back to the picture of effect of temperature, we talk about slight extensions. Since we are still in the discussion of temperature, let's talk about the temperature influences and involve some amount of thermodynamics. It's as follows. So log K2 by K1, that's what we have derived. Log K2 by K1 is equal to EA by 2.303 R if it is to base 10, T2 minus T1 by T1 T2. So K2 by K1 is nothing but R2 by R1. It can also be taken as R2 by R1. This can also be taken as, if it is a first order, I can also take it as K2. K2 is 0.693 by T half 2 at a temperature T2. K1 is equal to 0.693 by T half 1 at a temperature T1. So when I substitute 0.693 by that discussion, then what will I get? I'll be getting T half 1 by T half 2. T half 1 is at a temperature T1. That is at a temperature T1. T half 2 is at a temperature T2. So like that. But for second order, I can't substitute directly like that. Kt half is 1 by A. K is equal to 1 by AK. So K is equal to 1 by AT half. So you have some problem in knowing even the A values and then substituting and simplifying. Generally, this should be highlighted in second order. If it is same, then also you can do the same way. It need not be highlighted because T half is independent of initial concentration for a first order. So I can blindfold substitute that. But that condition has to be verified before substituting it for the second part. So that's what we have when we talk about K. Now let's connect kinetics and equilibrium. So when I talk about connecting kinetics and equilibrium, it goes in the following way. That's what we have as R giving rise to products. Kf is the rate constant for forward reaction. Kb is the rate constant for backward reaction. So Kf and Kb can be written like this. Kf is equal to Af into e power minus Ea by Ea for forward reaction by RT. Kb is equal to, I am using Arrhenius equation for forward and backward reactions. I am using Arrhenius equation for forward and backward reactions. Next, let's talk about how do you write equilibrium constant for this particular reversible reaction. K equilibrium is equal to Kf by Kb. So Kf by Kb, and then I can rearrange that. So that's what we get. K equilibrium is equal to Kf by Kb is equal to Af by Ab into e power minus Ea of forward reaction by RT divided by e power minus Ea of backward reaction by RT. When we take the exponential part to the numerator, I took Kf by Ab as A equilibrium. Sir, K equilibrium is products by reactants. Yes, it's a concentration of products by concentration of reactants. Since I'm talking K equilibrium, it can be Kc, then I'll be getting this. If it is Kp, then I'll be calculating pressure in terms of pressure. So that you have to be knowing. Next up. So let's confine ourselves to these things, connecting kinetics and the equilibrium rather than the concentration. So equilibrium constant is equal to A equilibrium into e power minus Ea forward reaction, which is of the numerator. This becomes plus. Now we know very clearly one point yesterday in the previous class. Activation energy for forward reaction minus activation energy for backward reaction is called delta H. So I'll be calculating, I want to substitute delta H here and connect kinetics to equilibrium and then to thermodynamics. So how? This is how I'll be substituting. K equilibrium is equal to A equilibrium into e power minus, when I take minus common, I'll get whatever I want in terms of delta H. Activation energy for forward reaction minus activation energy for backward reaction by RT. And then I'll be getting this K equilibrium is equal to A equilibrium into e power minus delta H by RT, where delta H is given by, we know that formula of delta H as activation energy for forward reaction minus activation energy for backward reaction. So the sign of this delta H has to change from endo, which is positive, to exo, which is negative, but not the formula. Formula should remain the same. So that's what we have. And then let's talk about connecting this equilibrium data with thermodynamic data. How? It's as follows. We know one thermodynamic equation, delta G is equal to delta G naught plus RT ln Q. Delta G is equal to delta G naught plus RT ln Q, where Q was reaction quotient. At equilibrium, delta G is 0. Delta G naught need not be 0. Most of the cases it won't be 0. Delta G is 0. So when delta G is 0, at equilibrium, delta G is 0. When delta G is 0, what will I get? I'll substitute 0 there and take this entire part to the other side, so that I'll be getting delta G naught is equal to minus RT ln K equilibrium. We know very clearly what is delta G. Delta G equal to delta H minus T delta S. Similar way, delta G naught is dash delta H naught minus T delta S naught. So I can substitute that here. So delta H naught minus T delta S naught. I'll take minus RT to the other side. So that what do I get? Log K equilibrium. I'll take minus RT to the other side. Log K equilibrium to base E is equal to delta H naught minus T delta S naught by minus RT. I'll expand the numerator, so that I'll be getting minus delta H naught by RT. The T is being taken out as 1 by T. That minus has come from the denominator. Now when I remove this, I'm left off is minus T delta S naught by minus RT. Minus minus gets cancelled, T gets cancelled. So plus delta S naught by R. So what did I get? Log K equilibrium to base E is equal to delta S naught by R plus of minus delta H naught by R into 1 by T. When I convert this to, so that's what we get. But be careful, this is not rate constant. It is ratio of rate constant of forward reaction to backward reaction. That is an equilibrium constant. This is an equilibrium constant that we are talking. We have a similar equation even for kinetics also. What is that? Log rate constant to base E is equal to minus EA by R into 1 by T plus log A to base E. So that's what we get. Now continuing further, when I want to write K equilibrium, this E goes to the other side. So what will I get? I'll be getting this part. K equilibrium is equal to E to the power this plus that. Means E power this into E power this. So E to the power delta S naught by R into E to the power minus delta H naught by RT, which is equal to Kf by Kb. This is an equilibrium constant, capital K. These two are small k's that we have written. Capital K equilibrium is equal to small kf by small kb. Rate constant of forward reaction by rate constant for backward reaction, which is equal to concentration of the products to concentration of the reactants if it is Kc, as per 1:1 ratio that I have given, or if it is Kp, changes accordingly. So that's what we have, connectivity between thermodynamics and equilibrium. Let's continue with connecting it to the kinetics story. So what do we have in kinetics? In kinetics, log K2 by K1, these two are small k's that we have written. Log K2 by K1 to base E is EA by R into T2 minus T1 by T1 T2, because it was K2, so you wrote T2 minus T1. If it were to be K1, then you would have written T1 minus T2 by T1 T2. Net sign remains the same. A similar equation can be established even for equilibrium constant, which you did in your first year thermodynamics and chemical equilibrium. That is log K2 by K1. Log capital K2, K equilibrium 2 by K equilibrium 1 to base E is equal to delta H. Now delta H will come. Delta H naught by R into T2 minus T1 by T1 T2. Similar reaction will be there, similar equation will be there even for the thermodynamics. So log, this is capital K2 by capital K1, means I am talking about equilibrium constants, is equal to delta H by R into T2 minus T1 by T1 T2. There is a big difference in the two. What is that big difference? EA is always a positive value, but delta H can be positive, can be negative. I have the two cases now. Delta H can be positive, delta H can be negative. So if it is positive, and if you increase the temperature from T1 to T2, when this is positive, K2 greater than K1, when will this be positive? Provided endothermic. So for endothermic case, with rise in temperature from T1 to T2, K1 increases from K1 to K2, or you can say equilibrium constant increases from K1 to K2. But if delta H is negative, I'll repeat, if delta H is positive, if temperature is increasing from T1 to T2 such that the numerator is a positive value, numerator is positive, bracket is positive, this is positive, so this complete right hand side is positive, so K2 is greater than K1, only then I can get numerator greater than denominator, so this is greater than 1, so log value is a positive thing that we are talking. Means what? With rise in temperature, equilibrium constant increases provided you are talking about endothermic. With rise in temperature, if it is exo, the story is totally different. With rise in temperature from T1 to T2, if it is exo, means delta H negative, complete right hand side is negative. Complete right hand side is negative provided you have numerator less than denominator. This value is less than 1. So denominator is more than the numerator, means with rise in temperature from T1 to T2, equilibrium constant dropped for exo. Whether it is exo or endo, for kinetics is the same story. Always with rise in temperature, K rise, because that is positive. So that's what we have as the points to note. So for exo and endo discussions does not arise in kinetics. The difference of exo endo arises only in the thermodynamics part. So with rise in temperature, what did I write? Exo and endo important only in K equilibrium, not for K. Why? With rise in T, K rise. Finish. It's a small K that I have written. Whereas with rise in T, equilibrium constant for endothermic rises, whereas equilibrium constant for exothermic drop. Sir, which endo, which exo? Forward endo, forward exo. If forward is endo, then you call that equilibrium is exo. If forward is exo, then you say equilibrium is exo. If forward is endo, then you say equilibrium is endo. So like that, it will change. So that's what we have. Let's continue with the few problems for today. We'll take up something like 8 to 10 problems in this entire session. This problem solving session requires some support, you need some support from either log table book or the calculator. Sir, in the exam calculator is not allowed. Yeah, it's not allowed, but the problems that I am going to pick up now, it's a mixture of mains, advanced and the old advanced methods. So there are certain supportive things which you need, preferably in the form of log tables, but takes a lot of time. So it's left here. So as of now, let's start with the first problem. So you can take down. So I wrote this point just to give you a clarity. In equilibrium, you learned very clearly as well as in thermodynamics that with rise in temperature, equilibrium constant rise for endo, drops for exo. But that is not applicable for a rate constant K. With rise in temperature, rate constant Kf increases, rate constant Kb also increase. So both rate constants increase. Sir, but sir, we learned in Lee-Chatler principle that with rise in temperature, equilibrium moves in the direction of endothermic, no? Yeah, that's right. Because whatever direction is endo, the increment in the K in that direction is more than the increment in the exo direction. So the position moves in the endothermic supportive direction. So those things you refer Lee-Chatler principle. So as of now, with rise in temperature, Kf increase, Kb increase. Whichever is endo, there the increment will be more. So it is endo, then it rises. If forward is exo, then backward Kf rises, backward Kb rise a lot. Thereby, you say exo drops. K equilibrium for exo drop. So that's about the point. So just refer the thermodynamics part also. It's just revision. Anyhow, this is not applicable for our kinetics data, but analogous discussion. This is what you have a similarity in the two. EA cannot be negative, but so let's start with the first problem. Take down the first problem. For a reaction obeying first order kinetics, this is what we have. Log K to base 10, where K is measured in per second, is equal to minus 40 by T plus 20. Log K to base 10 is minus 40 by T plus 20. Determine Arrhenius parameters. Determine Arrhenius parameters. Determine Arrhenius parameters. So what exactly we mean by Arrhenius parameters? I'll read the problem again. For reaction obeying first order kinetics, log K to base 10, where K measured in per second is given minus 40, this is 40, minus 40 by T plus 20. Determine Arrhenius parameters. What are Arrhenius parameters? Yes, collision frequency factor A and activation energy. So you have to find those two. You are given this equation. Find A and activation energy, capital A and activation energy. So when I write that equation in the known form, this is what we know, log K to base 10 this is what we have as log K to base 10. So log K to base 10, because base 10 is given, log K to base 10 is minus EA by 2.303 R into 1 by T plus log A to base 10. So find them proportionately. When we know we have drawn a graph here, when I draw a graph, this is y is equal to mx plus c. This is a y-intercept. That y-intercept is given as 20. It's a slope which is given by minus EA by 2.303 R. What is the slope given here? Whether 40 or minus 40 by T. Slope is just minus 40. So I have minus 40 as a slope. So equate minus 2a by minus EA by 2.303 is equal to minus 40. And we have log A to base 10 as 20. So let's talk about this first. We are supposed to be finding Arrhenius parameters. So we are supposed to be finding Arrhenius parameters. Log K to base 10 is minus EA by 2.303 R into 1 by T plus log A to base 10. So A should be found. How can I find this? I can relate log K versus 1 by T graph y-intercept. What is the y-intercept of that particular graph? Is 20. So log A to base 10. Log A to base 10 is 20. A is equal to 10 power 20. That is, that many number of collisions are possible in 1 second in unit volume. In unit volume. Next, what do we have? I'm supposed to be calculating Arrhenius parameters, which one parameter is obtained, which is collision frequency factor. Actually, A is A into P into Z, but P doesn't have a formula, so we related A as a collision frequency factor itself. And then how do we go along and calculate activation energy? I relate minus EA by 2.303 R with minus 40. So that's what we get. Minus gets cancelled. Activation energy is equal to 40 times 2.303 R. So I substitute a proper value and unit for R. You will be getting respective activation energies. So that's what we get. So you know very clearly, I said in the previous class itself very clearly that activation energy and R have to be properly matching their units. So I know I'll be getting erg per mole per Kelvin if I substitute this. So this will be ergs per mole. If I substitute in joule per mole per Kelvin, this will be joule per mole, because that Kelvin part, that per Kelvin with the Kelvin here will balance. So I don't have to have, I will not have that Kelvin here. So if I substitute 1.98 or approximately 2 calorie per mole per Kelvin in R, then I'll be getting respective activation energy as calorie per mole. So that's about calculation with respect to for the first problem. So we calculated Arrhenius parameters. So what are the Arrhenius parameters that we have? A and EA. I've shown you the substitutions also in the previous class itself very clearly. Now I'm just using them and continuing. Now let's do one more problem the same. Calculate K at 127 degrees Celsius in above problem. The same first problem. Calculate K at 127 degrees Celsius in above problem. The same problem can also be given in a slightly different way as follows. The slope of the graph drawn between log k to base 10 on y-axis versus 1 by t on x-axis is minus 40 and y-intercept is 20. Then find Arrhenius parameters. What can be this problem also as? For a graph with log k to base 10 on y-axis versus 1 by t on x-axis, the slope is found to be minus 40 and y-intercept is found to be 20. Calculate Arrhenius parameters. The problem can be like that also. So continue. So calculate k at 127 degrees Celsius in above problem. How do we determine k? So at 127 degrees Celsius, so convert it to Kelvin. Substitute here, get log k. Find the antilog of it, you will be getting k. The substitutional part is this. That's what we have. Log k to base 10 is minus 40 by 100, minus 40 by 400, plus 20. So this turns out to be 0.1, is 20. So that's what we get as log k to base 10. K is 10 power 19.9. Let's find the respective antilog of that and then answer the k value, which is measured in per second. That's what is given here. So let's go to the second problem. See the second problem. That is the second problem. I said already, I need either logarithmic table to solve or some scientific calculator will support you for this class. We'll be doing some advanced substitutions also, just like our experimental data problems. Here also we are doing similar discussion. Simplified numbers cannot be given always, but in exam for the past decade, it's not always true. So you have to be cautious. Base 10 by d 1 by t. D log k to base 10 divided by d 1 by t is minus 5 and y-intercept is 0, 4. Then A, plot the graph. Arrhenius factor A equals to dash. Arrhenius parameter activation energy is dash kilojoule per mole. And determine Boltzmann factor at 27 degrees Celsius. Arrhenius factors were A and DA. Determine the Boltzmann factor. What exactly the Boltzmann factor? Fraction of active molecules. We are talking about fraction of active molecules here in the Boltzmann factor at 27 degrees Celsius. So determine these things. 2 minutes will be given. Understand that dy by dx properly and substitute and simplify. So what do we get? What is this y-intercept giving us? What exactly is the graph first of all? It is dy by dx, right? So d log k to base 10 versus d 1 by t. So what am I supposed to be taking? Which equation am I supposed to be taking? Same. Again, I'll go back to the same equation, which is log k to base 10 is equal to minus Ea by 2.303 r into 1 by t plus log a to base 10. I'll start with the same equation and then I'll plot a graph. What exactly is the graph that we are getting? Log k to base 10 versus 1 by t. That's a graph because slope will be a negative minus Ea by 2.303 r into 1 by t. So that slope is given by dy by dx. So slope is given by this minus Ea by 2.303 r, which is minus 5. When slope is minus 5, E by 2.303 r is nothing but 5. We need activation energy. That's what is asked per Kelvin. So 8.314 into 10 power minus 3 kilojoule per mole. per Kelvin. So substitute and simplify. What is to be substituted in R? 8.314 into 10 power minus 3. 5 into 2.3 into 8.314 into 10 power minus 3 will give me activation energy. I'll be getting activation energy in kilojoule per mole. That's what they asked here, in kilojoule per mole. Then how do we calculate the second bit? That comes from the y-intercept. Y-intercept is given as 0,4, or 4 is the y-intercept. That is nothing but log a to base 10. So a is equal to 10 power 4. That many number of collisions per unit time per unit volume. Now what are we asked in the fourth bit? We are asked to find Boltzmann factor at 27 degrees Celsius. What exactly is the Boltzmann factor? It's a fraction. Why are we saying fraction? 1 divided by this entire part. So how to calculate? Apply log. Determine this in a simplified form. Anyhow, they have given EA minus EA by 2.303 RS minus 5. So what is EA by R? It's 5 times 2.303. So divided by 5 times 2.303 divided by temperature. They said temperature as 27 degrees Celsius divided by 300. So that's what we get as the power. So that's a Boltzmann factor. That is about the Boltzmann factor. So e to the power minus, what is activation energy? EA by R. Now I'll substitute EA by R directly from here, as EA by R equal to minus goes, so 5 into 2.303. 5 into 2.303 by T. T as 300. Simplify this, or else apply log on both sides, get this value in a simplified way, and then find the anti-log of that, so that log F will change itself into F. F will give you this answer. Either they may give you this in terms of this, or they may convert it to the respective number and give you. For this conversion, you don't have to panic about how to convert this to a given 10 power something or 2 power something. So that support will be given, or else direct answers are asked for the past almost 5 to 6 years. Directly will be answering. So that's about the second problem. So in the first and second, we are relating ourselves to the influence of temperature on rate constant K. Influence of temperature on rate constant K. Now let's continue with the same even further, because the catalyst part is relatively easy. This is the one which will have some calculations also to take care. So let's continue. Let's take up this third problem. Temperature coefficient of a reaction is 2. Temperature coefficient of a reaction is 2. Temperature coefficient of a reaction is 2. Then calculate activation energy of the same reaction in the vicinity of 32 degrees Celsius. In the vicinity of 32 degrees Celsius. What is meant by vicinity of 32 degrees Celsius? We'll talk. Calculate the activation energy of the reaction in the vicinity of 32 degrees Celsius in kilocalorie per mole. Now, what is meant by vicinity of 32 degrees Celsius? We know very clearly temperature coefficient means Kt plus 10 by Kt. Kt plus 10 by Kt. Generally, I said T is 25 plus 273. 25 degrees Celsius plus 273. 298 Kelvin. The T is 298 Kelvin. So 308 Kelvin. But here we just approximated it. Instead of 25, in this vicinity, in the sense 27 plus 5 is this plus 5 is the next. So 27 to 37 are lower and higher temperatures. So simplify this problem. I know K2 by K1 as 2. Temperature coefficient. Okay, fine. Let's write those points first. Gamma, which is the temperature coefficient, Kt plus 10 by Kt, is given as 2. So 32 degrees Celsius in the sense, in the vicinity of 32 in the sense, I have to create 10 degrees around 32. So 5 lower, 5 higher, 27 to 37. That's a T1, this is a T2. Corresponding to T1, I have this. Corresponding to T2, I have that. We were dealing directly with at a given temperature. In these two problems, in the first set of two problems, we have dealt with a single temperature. We dealt with a single temperature, but that is made variable, but that's again a single temperature discussion itself. So on a single equation with log K2 by K1. Sir, temperature coefficient can also be R2 by, yeah, that's also a ratio of rates can also be written here. So substitute this and simplify. Where to substitute, why, how to, you know it now. So that's what we have. K2 by K1 is equal to EA by 2.303R because the base is 10, 2.303R. Since it is K2, it is T2 minus T1. If it were to be K1, then T1 minus T2 by T1 T2. So that's what we have. I know already this is equal to EA by 2.303R. R has to be in kilocalories, so 2 into 10 power minus 3 into T2 minus T1. K2 related is T plus 10. T plus 10 means this, which is 273. When I add 273, I'll be getting 310. 310 minus 300 by 300 into 310. So what is activation energy? Activation energy is 2.303. Now I'll be getting activation energy directly like this. Activation energy is equal to, this is log 2 to base 3. 2 into 10 power minus 3 is giving me kilocalorie per mole. T1 T2, when this goes to the other side, because activation energy is what I want, this goes to the other side, T1 T2 by T1 T2 minus T2. T2 minus T1. So 310 into 300 by 10 degree will give me activation energy, which is 12.9 kilocalorie per mole. So I'll be getting close to this 12.9 or 13 kilocalorie per mole. So temperature coefficient is given in the vicinity of 32. They asked us to find the activation energy. Fourth, this is what I was talking. We need some support from the logarithmic tables or the calculator. 4, 5, 6, 7, 8 especially. Yeah, take down the next problem. The rate constant of a reaction is 1.5 into 10 power 7 per second at 50 degrees Celsius. The rate constant of a reaction is 1.5 into 10 power 7 per second at 50 degrees Celsius. And 0.693 by 4.5 into 10 power minus 7 second is the half-life at 100 degrees Celsius. And 0.693 divided by 4.5 into 10 power minus 7 second is the half-life at 100 degrees Celsius. This is the half-life at 100 degrees Celsius. Calculate Arrhenius parameters. Calculate Arrhenius parameters. Think about this. See the two different temperatures. It's not a one single temperature, it's a two different temperatures. So obviously, the rise in temperature, drop in temperature, one is a K, the other one is a T half. So we have to be looking at all those points and then substitute and get the respective activation energy. From activation energy, we have to be going to the other Arrhenius parameter, collision frequency factor A. So substitute these things and simplify. Substitute those things and simplify.